Hey everybody, welcome to our sixth review of the Energy Systems Engineering Masters webinar series. Today we will be discussing the talk titled Global Energy Transition, Challenges and Strategies. This talk was hosted by two guest speakers from EPRI, Michael Caravaggio and Stephen Storm. Michael is Director of the Generation Sector, and Stephen is an Area Manager of Fleet Generation Optimization. Michael provided an overview of challenges facing the global U.S. grids as we move towards a net zero future. Stephen focused on the strategies needed to adapt our grid to net zero. Michael began his talk by outlining some of the global challenges we've seen with our energy transition. I'd like to pass it over to Joby to discuss some of these points. Joby, what global energy challenges have we seen in this past year?
Thank you, Alex. Within the past year, we have discovered 8 different global challenges. Grid adaptation for net zero, transitioning the existing energy grid to support a net zero future presents significant challenges. This involves integrating more renewable energy sources while maintaining reliability and efficiency. Balancing energy supply and demand. As we shift towards renewable energy sources like wind and solar, which are intermittent by nature, balancing supply and demand becomes more complex. Energy storage and management. Efficient and large scale energy storage solutions are crucial to address the intermittent nature of renewable energy sources and ensure a steady energy supply. Infrastructure upgrades, upgrading the existing energy infrastructure to support new technologies and higher loads due to the electrification of sectors like transportation. Economic and policy challenges, implementing the transition requires significant investment in supportive policy frameworks. Balancing the economic impacts, especially in regions reliant on traditional energy sectors. Global collaboration and standards. The energy transition is a global effort requiring international collaboration and the establishment of common standards and practices. Technological innovation. Continuous technological advancements are needed to improve the efficiency and feasibility of renewable energy sources. Environmental impact, minimizing the environmental impact of new energy infrastructures like land and resource use for solar and wind farms is a significant consideration.
Good answer, Joby. Bringing our attention inward, Ava, what challenges have we seen in the United States during extreme weather?
Thanks for the question, Alex. So the U.S. has certainly experienced some challenges on the grid in the past few years, given some extreme, winter storms and other extreme weather events, being some pretty significant ones. So the U.S. is, we join the rest of the world in having some grid issues and issues in the energy transition in general. So in February of 2021, Winter Storm Uri hit Texas pretty hard, causing electricity generation failure. So the aging dispatchable generation assets that ERCOT, the grid operator for Texas, had, combined with the number of variable assets that had intermittent generation, led to an imbalance of electricity supply and demand. So as the frequency on the grid dipped because of this, millions of homes lost power. Even though they came within 4 minutes of an entire grid collapse, the outages that still happened still resulted in over 200 deaths, and the cost of the incident is expected to reach $300 billion. So pretty big impact, definitely a tragic scenario that happened. And then about a year ago, the East Coast was rocked by Winter Storm Elliott, and it brought its brutal winds and bitter cold. And there was a record-setting 90.5 gigawatts, or 13% of the generating capacity of the Eastern Connection, which is the grid system that covers 2/3 of the US, had failed. So almost 91 gigawatts failed to run or operated at reduced capacity during the storm. The gas-fired capacity accounted for 63%, 63% of the outages, and the next highest one was coal and lignite, so both fossil fuel sources. During extremely cold temperatures that happened, during Winter Storm Elliott, cold temperatures, basically what happens during this is the gas supply is a common mode of failure when it's too cold. And according to FERC, 55% of the outages and failures, so over half of the outages and failures, were due to freezing and fuel issues. So on one hand, freezing temperatures impair the grid's reliability. For example, during Winter Storm Uri, Winter Storm Elliott, And then on the other hand, we have extreme heat waves that had hit the West Coast, and that also caused forced outages and negatively impacted the grid. So California experienced energy emergencies during these times of extreme heat. CAISO, a grid operator for California, or independent system operator in California, with a significant amount of renewables in their generation portfolio, believes that renewables were not to blame for the outages, but rather that the real problem was a statewide failure to assemble the right energy mix of energy sources for the completely predictable situation of energy demand staying high after the sun goes down. So, still impacted by renewables, but they want to be clear that the cause of the issue was not renewables themselves, which is kind of a iffy statement to make. But as extreme weather events continue to happen, and they will continue to happen because of climate change, it becomes increasingly important to maintain a reliable grid that can function well with intermittent variable generation, combined with a decreased reliance on fossil fuels. All right, back to you, Alex.
Thank you, Ava. Grid operators are working tirelessly to make our systems more reliable given these set of challenges. Ahmed, let's shift our attention back to the global energy market. How are different countries growing their grids? What are the technical and environmental risks associated with these strategies?
When the Biden administration announced that the United States had formally rejoined the Paris Agreement in February 2021, it underlined the global nature of efforts to reduce greenhouse gas emissions and decarbonize the world economy. Up to now in the United States, decarbonization has been driven by market forces and quickened by cheaper and more competitive costs of renewable energy. Wind has become the fastest growing segment of the renewable energy market. The International Energy Agency reported that some 74% of United States coal-fired plants produce electricity at higher costs than if they were replaced with renewable sources. The Paris Agreement establishes a global framework to limit increases in global temperatures to less than 2 degrees Celsius, above pre-industrial levels. Industrial countries are now settling goals of becoming carbon neutral by 2050. It's a heavy lift. The Aspen Institute defines a challenge for zero carbon technologies to make a big dent in emissions level. They have to become almost ubiquitous in a relatively short period of time, which will require harnessing the power of markets and the grid to get capital flowing. It's hard to say whether all the technologies needed to tackle the climate crisis already exist. Either way, innovation would certainly make tackling the challenge easier. The Green Future Index, a new report compiled by Technology Review Insights and others, ranked 76 countries on their efforts toward decarbonization. 15 European nations ranked in its top 20, with Iceland, Denmark, and Norway at the top. Countries ranked near the bottom include South Africa, Vietnam, Indonesia, and Japan. Although Japan does have a 2050 carbon neutral goal, Russia continues to concentrate on fossil fuels. Germany's Climate Change Performance Index follows decarbonization by country closely, with similar rankings. Here is where 5 major countries are in the race toward decarbonization. The United States ranked dead last in the CCPI report. It was a repeat of its previous year ranking, solidified by withdrawing from the Paris Agreement and the lack of national targets to reduce emissions or increase renewable energy capacity. Per capita emissions did continue to fall, but were driven by individual states and cities, combined with the continuing push away from coal based on market conditions. Falling renewable energy costs also boosted their growth, but emissions still remain high, as does per capita energy use. The National Academy of Sciences issued a report last year detailing what the United States needs to reach 2050 decarbonization goals. First, electricity generated by non-carbon emitting sources needs to be doubled to at least 75% by 2030, an effort that will require record-setting deployment of solar and wind technologies, along with scaling back coal and natural gas-fired power plants. Second, by 2030, 50% of new vehicle sales should be zero-emission vehicles. The country should replace 20% or more fossil fuel furnaces in buildings with electric heat pumps and set policies so new construction is all electric except in the coldest areas. The grid needs expansion and bolstering. The report calls for a 40% increase in electrical transmission capacity by 2030 to better distribute wind and solar power from where it's generated. At the same time, it calls for a build-out of an electric vehicle recharging network and the nation carbon dioxide capture, transport and disposal network from point sources. Also, total energy used by new buildings should be reduced by 50% by 2030. The new Biden administration is expected to accelerate work toward decarbonization and re-enter the Paris Agreement as one of its first acts. China ranked 30th in CCPI's ranking and very low in emission reduction compared to other countries. China remains the world's biggest emitter of greenhouse gases, although President Xi last year promised his country would bring emissions to a peak before 2030 and become carbon neutral by 2060. To do so, the country will begin promoting large-scale carbon capture projects and track methane emissions from coal, oil, and gas extraction. China's continued use of coal remains a concern and is inconsistent with the Paris Agreement, according to the United Kingdom Climate Action Tracker. By mid-2020, China permitted more new coal capacity than in 2018 and 2019, bringing total coal capacity in the pipeline to 250 gigawatt bring 10 gigawatt of new plants online. China is going against the global shift away from coal and now possesses roughly half of the world's coal-fired power plants in development. Still, China is on track to achieve its 2030 peaking target of emissions, partly because the COVID-19 pandemic forced closures and lowered emissions. Climate Action Tracker calls it critical that China uses stimulus programs to clamp down on what may be the start of a new coal boom and dedicate recovery efforts to low emissions infrastructure and clean energy projects. Germany was one of the first countries to adopt the Climate Action Plan under the Paris Agreement, but has mixed reviews in implementation. The CCPI reported its high per capita greenhouse gas emissions and energy use, along with growing transportation emissions, are concerning. But in 2020, it put into law plans to phase out coal-fired power generation by 2038 and passed another bill that sets a carbon price on transportation and heating. The country has progressed in expanding renewable energy sources, with more than 40% of power consumption supplied by renewable in 2019. Its goal is to increase it to 65% by 2030. But the share of renewable in gross final energy consumption is 17.5%, considered low. The International Energy Agency reported last year Germany is not on track to meet near-term emissions reduction targets. It was to have reduced total greenhouse gas emissions by 40% by 2020, but fell short by 9%. But it notes that the energy sector has supplied the bulk of reductions and more needs to come from transportation and heating in the building sector. There are efforts for the government to promote rail transportation over vehicles as a way to further reduce emissions, The government wants to put 10 million electric cars on German roads by 2030. But a recent report by Deloitte reported a more visible number of 6.35 million by that time.
Thanks, Ahmed. That's very thorough. It's interesting to see how each country is tackling their climate goals in different ways. In their discussion, Michael and Stephen both highlighted the perfect storm of challenges we face as we transition our grid. They both harped on the need to make generation affordable and resilient. To do this, we need to overcome various levels of uncertainty between the technology we currently have and the technology we need to get to net zero. With the introduction of intermittent distributed generation, demand management, and vehicle electrification, our grid is getting more complicated. It took us 80 years to build out the coal fleet we have today. We have a mere 27 years between now and 2050. By 2050, our grid will look drastically different than it does today. Ava, in order to get to net zero by 2050, we need to utilize a lot of different technology. Currently, we're banking on tech that is not commercially viable. What do you think some of the biggest gaps in our tech are?
So there are a few key areas where we're still playing catch up on the road to net zero. Energy storage is a big one. We need better and more efficient ways to store renewable energy for when the sun isn't shining or the wind isn't blowing. Batteries specifically, they've come a long way, but there are many remaining challenges that revolve around energy density, the cost of it, and resource availability. Batteries need to store more energy, essentially, in a smaller and lighter package. This is essential for electric vehicles to have longer ranges and for renewable energy systems to store this excess energy generated during peak production times that's then not consumed at that time. While the cost of batteries has decreased significantly, it's still a factor hindering widespread adoption. Further cost reductions are definitely needed to make large-scale energy storage economically viable. In terms of resource availability, the production of lithium-ion batteries relies heavily on materials, obviously like lithium, cobalt, and nickel. Securing a stable and ethical supply chain for these resources is a big challenge, and researchers are exploring alternative materials that could potentially mitigate some of these concerns. We're still looking into better ways to recycle these batteries when they reach the end of their lifetimes as well. So another gap in technology is surrounding carbon capture and storage, or CCS. So, finding scalable and cost-effective solutions is crucial for reducing emissions from existing industries. In terms of cost, though, CCS technologies are currently expensive to implement and operate, so there's a need for significant cost reductions to make them more economically feasible for widespread use. Developing secure and reliable storage sites for captured carbon is another challenge. Identifying suitable geological formations for long-term storage without the risk of leakage is crucial. And we're still, not entirely sure of the long-term environmental effects of this technology either. And finally, for CCS, the lack of consistent policies and regulations supporting its implementation hinders its widespread adoption. So it's kind of a common trend we see. We need more recent and updated regulations for some of these solutions. The highlights, again, just like I said, this highlights the importance of needing governments and industries to work together to create a favorable environment for investment and deployment, and working with or through regulations. And then, of course, advancements in sustainable transportation technology, like electric planes, long-range batteries, those are still in the works because the transportation sector has a pretty far ways to go until it's completely decarbonized. So overall, it's a bit like assembling a giant puzzle. We're hunting down for those missing pieces and trying to figure out how everything will fit in to hopefully reach our net zero goals, not too far past the deadline that we set, hopefully in the somewhat near future.
Good points, Ava. We're very interested to see how carbon capture and sequestration develop in the coming years. It's clear that we can't eliminate fossil fuels from our grid. That said, we're asking these assets to cycle more frequently to keep up with fluctuating production. Mohammed, can you explain why increasing the cycling and flexibility on natural gas and coal power plants reduces reliability of the plants?
Yes, Alex, of course. Increasing the cycling and flexibility of natural gas and coal power plant can reduce their reliability because it put more stress on essential part. The power plant are designed to work in the best condition with steady state and continuous operation. When we make them start and stop frequently or handling a change in the peak demand, it put more wear and tear in the important part like turbines and boilers. The quick change in the temperature during a cycle can cause problem, especially for the component like boiler tubes. The plant become less efficient and at maintaining optimal combustion condition during varying the load, leading to high fuel consumption per unit electricity. Erosion and corrosion will be speed up with coal ash and sulfur content of the natural gas, causing material deteriorated. Handling the dynamic change in the load condition require advanced control system, and if they are not well designed or maintained, it can lead to operational problem and unexpected shutdown. Overall, while flexibility is necessary, it brings significant challenge to the reliability of the natural gas and coal power plant.
Thanks, Mohammed. Sounds like there's a lot of work to be done to bring these assets up to speed. Ahmed, how does the design of the asset impact its ability to be both flexible and resilient? What are some of the challenges associated with cycling an asset that was originally designed for baseload power?
Million by that time. Thank you. Competition and increasing penetration of variable renewable generation are having a far-reaching impact on the operation of conventional fossil generation. For many utilities and plant operators, plant operations and maintenance expenditures are the one cost area that is currently rising at a rate faster than inflation. To stay competitive, utilities need to better understand the underlying nature of their plant operation and maintenance costs, and they take measures to use this knowledge to their advantage. A major root cause of this increase in operation and maintenance costs for many fossil units is unit cycling. Power plant operators and utilities have been forced to cycle aging fossil units that were originally designed for base load operation. Cycling refers to the operation of electric generating units at varying loads level, including on-off load, following, and minimum load operation, in response to changes in system load requirements. Every time a power plant is turned off and on, the boiler, steam lines, turbine, and auxiliary components go through unavoidably large thermal and pressure stresses, which cause damage. This damage is made worse for high temperature components by the phenomena we call creep fatigue interaction. While cycling related increases in failure rates may not be noted immediately, critical components will eventually start to fail. Shorter component life expectancies will result in higher plant equivalent forced outage rates, EFOR, and or higher capital and maintenance costs to replace components at or near the end of their service lives. In addition, it may result in reduced overall plant life. How soon these detrimental effects will occur will depend on the amount of creep damage present and the specific types and frequency of the cycle. Several renewable integration studies have recognized increased power plant cycling due to renewables. Additionally, most reports also list the need for more flexible generation in the generation mix to meet the challenge of ramping and providing reserve requirements. There is still a cost to cycle such plants. Modern combined cycle plants also have constraints with heat recovery, steam generation, reliability, and have a cost to cycle. Asset management of a fleet must include all the costs, including cycling costs, some of which are often latent and not clearly recognized by operators and marketeers. Most small and especially large coal units were designed for base load operation and hence, on average, are higher cycling cost units. Thermal differential stresses from cycling result in early life failures compared to base load operation. There are some important economies of scale for large coal and other fossil units that lower their costs. So the highest costs per megawatt capacity occur in some abused smaller coal units, especially for cold starts. Once all operating costs, including cycling, are accumulated for, the best system mix of generation can be matched to changing loads and market opportunities. Cycling start costs have a very large spread of variation. Median cold start cost for each of the generation types is about 1.5 to 3 times the hot start, capital and maintenance cost. For the lower bound 75 percentile, this ratio of cold start cost versus hot start cost is only slightly higher. The gas aeroderivative combustion turbine unit have almost the same relatively low cost for hot, warm, and cold starts. That is because for many key components in this design to cycle units, every start is cold. Typically, large supercritical power plants are operated at base load and do not cycle much. Operating these units in cycling mode can often result in unit trips and cycling-related failures. As a result of the false starts and the trips, the real cost of cycling these units is significantly high. Moreover, these units cannot easily be brought online under these circumstances, and such factors are not fully captured in this data set. Older combined cycle units were a step change in lower operating costs due to cycling efficiencies, and were designed and operated as base load units. Changing markets have resulted in variable operation, and when operated in cycling mode, these combined cycle units can have higher cycling costs compared to a unit specifically designed for cycling, which can be seen from the distribution of costs. While a unit reliability during its early life has little indication of cycling damage and costs, long-term costs and life consumption that leads to failures reach a point of very rapid increases in failure rates due to cyclic operation. It could be seen a better statistical fit of cycling starts and costs when equivalent forced outage rates costs are included in the regression. There is an inherent trade-off relation between higher capital and maintenance expenditures and the corresponding lower equivalent forced outage rates. While this is not conclusive from the regression themselves, the huge variation impacts in these results may be attributed to this phenomenon. The higher operating and maintenance costs of supercritical units can be observed from the base load cost. Gas combustion turbine units were found to have the least base load cost, but these units typically operating in a cycling environment as peaking units, which have high total cost. Thank you.
That was very insightful, Ahmed. I think renewable energy's impact on the efficiency and health of our traditional assets is commonly overlooked. It seems like the United States legislature is pushing for a greener grid, but not fully supporting the utilities from a technical and financial aspect to handle the stresses put on their existing assets. Joby, when we add more renewables to our grid, we require our assets to be more flexible. Unfortunately, our most flexible assets emit the most amount of carbon. This means that we would like to run these assets as little as possible to make the grid the cleanest. How does cycling these assets and producing less electricity with them on a yearly basis impact their financial performance?
Cycling traditional flexible energy assets typically fossil fuel-based power plants, less frequently and reducing their electricity production to accommodate more renewables on the grid, have several financial implications. Reduced revenue from generation. The most direct impact is the reduction in revenue for these assets due to decreased electricity production. Since these plants are operated less frequency or at lower capacities, they generate less electricity to sell, directly affecting their profitability. Increased maintenance costs. Cycling power plants on and off or operating them at variable loads can lead to increased wear and tear. This irregular operation often requires more frequent maintenance, increasing operational costs. Moreover, these maintenance activities might be more complex and costly compared to steady-state operations. Capital recovery and fixed costs. Many traditional power plants have significant fixed costs, including capital recovery. Reduced operation does not proportionally reduce these fixed costs, leading to a higher cost per unit of electricity produced, affecting the financial viability of these assets. Market and regulatory factors. The financial performance is also influenced by market dynamics and regulatory policies. For instance, carbon pricing or emissions regulations can increase the cost of operating carbon-intensive assets, while subsidies or incentives for renewable energy can shift the market preference away from these traditional assets. Grid services and supplementary income. To mitigate some of these impacts, these flexible assets can potentially find supplemental income streams by providing grid services like frequency regulation, load balancing, and backup power, which are crucial in a grid with high renewable penetration.
Thank you, Joby. This is definitely something we will need to heavily consider moving forward as we reconstruct our energy markets. Mohammed, what is EPRI doing to help system operators and utilities make their assets more flexible?
Yes, of course. EPRI provides industries with the tools to manage flexibility and reliability in generating assets under variable conditions. There are 4 core areas that EPRI focus on. The first one is the training and awareness. The second one is providing operation and maintenance for the best practice. The third one is to make sure they have tools for systematic programming management. And the last is to have defense strategy in place to be alerted if there is any issue determined by human contact. Also, they are every focusing on transition to net zero goals. For example, the heat rate improvement in power plant improve the air emission and contribute to overall reliability and life of the power plant. Besides that, optimizing instrumentation for monitoring and advanced thermal power plant performance monitoring. Additionally, EPRI built the flexibility issue and solution database to reference for the operation of power plant, plus providing formats for high-level flexibility assessment to identify the opportunity of improvement.
Thanks, Mohammed. These projects are clearly needed to support our system operators. Well, folks, looks like we're going to have our hands full for the foreseeable future. If you're watching this and still deciding on a career, I'd highly recommend entering the energy industry. As you can see, there's a lot of work that needs to be done to make our grid reliable, resilient, affordable, and clean. That's all we got for today. See you next time. Take care.